Hi everyone, my name is Shijie. Here I'm representing our team to present sniffed, a practical approach to inject energy into 5G NR. Before diving into our framework, let's first look at the threat model. In 5G, both physical layer signals and messages exchanged before the security context is established remains unencrypted. This creates an opportunity for the attacker to intercept or spoof these messages and signals over the air. Most prior to assumes a man-in-the-middle attacker using a rogue base station. However, rogue base stations must broadcast the stronger signals to attract UEs, which makes them easily detectable. Also, there's lacking of tools for passive sniffing and spoofing the signals over the air between the base station and the UE. We define our attacker model as follows. We assume a passive or active attacker operating within the radio range of the target UE and the base station. For access level, the attacker does not have privileged access to the base station or the core network, nor do they possess the subscriber's credentials or cryptographic keys. However, the attacker is capable of eavesdropping on unencrypted messages, such as aNRchy setup and registration request. Additionally, the attacker can inject or replay messages over the downlink communication channel toward the UE. Based on the attacker model, we present our framework, sniffed, which is short for sniff plus 5G plus inject. First, sniffed can passively sniff both downlink and uplink messages, allowing us to track the UE's communication state in real time. On the right side, you can see an example Wireshark capture containing the downlink and uplink messages. Once a UE reaches a specific communication state, for example, right after the UE receives a particular message, sniffed can selectively inject or replay message using the overshadow technique. This enables us to transmit it at the exact same frequency and time as a legitimate base station. Because the UE cannot distinguish whether the message is coming from the legitimate base station or the attacker, it accepts and reacts to our injected message. This capability enables a range of attacks, including modem crashes, force downgrade to earlier generation, authentication bypass, and device fingerprinting. Let's now dive into the design of sniffed. The framework is composed of three major components. Firstly, the syncer. It runs cell search by searching and decoding the synchronization signal block, SSB. This allows it to get synchronized with the target base station in terms of time and frequency. Once synchronized, it also keeps tracking of the SSB block in case it lost the sync. Moreover, it captures and forwards subframes to other components for further decoding. Next, the broadcast worker. The broadcast worker components decode the system broadcast informations such as SIP1, which contains the information about the cell and the basic configurations for the UE to initiate the connections. After applying these configurations, the broadcast worker turns to detect random access response message from the base station. RAR message is the first message that transmitted from the base station to the UE after the UE initiates the random access procedure. Detecting and decoding this message allows us to detect the new UEs connecting to the target cell. When a new UE is detected, sniffed activates a UE tracker instance to monitor its interaction with the base station. The UE tracker keeps tracking the communication state and the UE-specific configurations. It includes a few components. The UE worker is responsible for decoding all the downlink messages sending from the base station to the UE. And the gNB worker is responsible for decoding the messages sending from the UE to the base station. Once the messages are decoded either by the UE worker or gNB worker, they are then passed to the exploit module, which is a flexible user-defined script. The exploit module first dissects the message, infer the communication state from the message sending between the base station and the UE, and determines whether it is the expected state to perform the attack. For example, if it detects a registration request message from the UE, it generates a registration reject message to the target UE. And finally, the gNB injector encodes the message generated from the exploit module. Next, it also generates the desired messages scheduling this downlink transmission, and then inject these two signals together to the target UE with a few duplications. Since the physical layer is unencrypted, the UE cannot distinguish if the message is coming from the base station. Thus, it accepts the message and reacts according to the attacker. Sniffed supports three categories of the attacks. Firstly, one-shot attack, where a single injected message can trigger an immediate reaction, such as crashing the UE modem or forcing a downgrade. Secondly, one-shot attack that expects a response, which allows us to do things like fingerprinting a device. And finally, multi-stage attack, which combines sniffing and injection across multiple communication states to enable more complex exploits, such as authentication replay downgrade. In the next few slides, I'll walk you through examples of each category. In the first scenario of one-shot attack, we leverage exploits identified in 5 groups. After sniffing the RC setup request from the target UE, Sniffjet enables a malformed RC setup message. Upon receiving this malformed message, the UE crashes immediately. In another example of one-shot attack, after sniffing the registration request message from the target UE, Sniffjet injects a spoofed registration reject message. When the UE receives this message, it ignores subsequent secret mode command from the legitimate base station and instead downgrade to LTE. Another scenario is one-shot attack that expects a response from the UE, which can be used for fingerprinting. In this example, when the attacker observes registration request from the UE, Sniffjet injects an identity request along with an uplink grant. Upon receiving and accepting this injected message, the UE responds with an identity response. In a multi-stage attack, the attacker continuously sniffs traffic between the target UE and the base station, injecting messages at different states multiple times. Here, we demonstrate the authentication replay attack as an example. After the UE sends a registration request, Sniffjet replays a previously captured authentication request. The UE responds with authentication failure, and Sniffjet then updates the sequence number and replays this message again. Once the UE's timer T3520 expires, it eventually downgrades to LTE and remains in this downgrade state for up to 300 seconds. We evaluated Sniffjet's sniffing capability using srsRAN. It achieves about 90% success rate in downlink sniffing and 70% in uplink sniffing. We also examined uplink sniffing performance over distance up to 20 meters across different phones. The success rate decreases slightly as the distance increases. Since Sniffjet leveraged timing advanced command to adjust uplink sniffing timing, we also evaluated performance across different TA offset. The result shows that uplink sniffing remains robust for TA variation of up to ±4, which corresponds to a time mismatch of ±1 microsecond. We also evaluated Sniffjet injection capability using srsRAN as a legitimate base station. Firstly, we measure the injection success rate with respect to the number of message duplications and at a different communication state. The result shows that the success rate increases as the number of duplication grows. Next, we evaluated injection performance over distance using a 30 dB amplifier. The result shows that Sniffjet can achieve up to 80% success rate at distance up to 20 meters. Finally, we validated the attacks on 4/4 5G devices using srsRAN and Effnet as legitimate base station, and we can achieve up to 40% success rate without an amplifier. Sniffjet is not only a tool for sniffing and injecting messages, but it is also highly reusable for several tasks. Researchers can evaluate attacks without a rogue base station, making tests more realistic. The DCI sniffing capability can be used for throughput analysis, measuring the traffic volumes over the air. And the message sniffing functionality allows detailed traffic analysis, which can be used for privacy research. Finally, the artifact provides pickup datasets during injection attacks, which can be leveraged for anomaly detection studies. Next, we'll show some demos of the sniffed framework.
Here, we'll demo 5Go attack to crash the UE modem. On the left side, we started Open5GS plus srsRAN as legitimate base station. The IMSI catcher is used to detect downgrade. On the right side, we project the UE screen. In the middle terminal, we run sniffed. We can open a new terminal to run ADB monitor. Next, turn off the airplane mode to trigger the UE to connect to the 5G base station. We can see we injected malformed aNRchy setup after receiving aNRchy setup request, and the aNRchy setup from the base station is ignored. In the ADB monitor, we can see as modem reason keyword is detected in the ADB log, which indicates the UE's modem has crashed. In this demo, we'll show authentication replay attack. First, we load the sniffer module to sniff the authentication request message. By toggling the airplane mode, we can trigger the UE to connect to the base station. Then we can copy the sniffed authentication request message, update the authentication replay module, and run build. Next, we restart sniffed and load the updated authentication replay module. Now turn off the airplane mode. The UE approaches the 5G base station first. We can see the UE send authentication failure a few times, and then it released the connection. On the IMSI catcher side, we can see the UE approaches the 4G base station while ignoring the 5G base station. Toggle the airplane mode and we can see the UE still approaches the 4G base station. The downgrade persists.